So we're going to prove the associative property of addition in V2, so for vectors in 2 space. Okay, and we're going to do this proof in what I call painstaking detail. Painstaking detail means I don't combine steps. Each step I take does one thing at a time. And I'm going to provide a reason for each step. Okay, talk a little bit more about painstaking detail once I've illustrated what I mean by that. Okay, if I'm going to be doing a proof, the very first thing I need to do is introduce the objects that I'm going to be talking about. So if I'm proving the associative property, I'm going to need to have 3 vectors in V2. So let's let we'll go with A, B, and C. Let's let A be A1, A2, be a vector in V2. Okay. I need all of that. I'm going to be doing the proof at the component level because these components are real numbers and I know stuff about real numbers. We don't know a whole lot about vectors yet, okay? But the statement of the associative property involves vectors. So I've got the name of the vector, I've named the components, and by saying this is in V2, that tells me that these guys are real numbers. If I didn't say that, I'd have to then say where A1 and A2 are real numbers. Okay, a lot faster to just say this is a vector in 2 space. I'm going to do the same thing for my other 2 vectors. Okay, so let's let B be B1, B2. That's also an element of V2. And let's let C be C1, C2. That's also in V2. Okay. Sometimes I'll see students just say, write C. They won't introduce this, but then they'll start writing this later on. I know what they meant. They mean this to be the components of C, but in a proof, it's your job to tell me. You cannot introduce a variable without telling me what it represents. Okay, so I have introduced this. Now, I'm going to write out what I'm trying to prove, but I'm going to clearly identify it as my claim. So my claim is that A plus B plus C is the same as A plus B plus C. Okay. Now, I clearly identified that as my claim because I don't yet know that it's true. This equation, you'll notice, has a left-hand side, which I'm just going to abbreviate as LHS for left-hand side, and it has a right-hand side. Very important in proofwriting, you can only work with one side at a time. It is not okay to work with both sides and simplify them simultaneously. Okay? Let me just show you one reason why that's so important. Okay? If I have an equation and I know the 2 sides are equal, I'm allowed to do the same thing to both sides. And we're so used to doing that, that if I've written an equation, it's going to be very tempting to change both sides. But if I do that, I could, quote unquote, prove something that's not actually true. Let me show you how. I think we can agree that this is not a true statement. -2 is not the same number as 2. But let's suppose I had that written down. I said, oh, it's written down, therefore it must be true. Excellent. This equation is true. Now I know I can do the same thing to both sides of an equation. So let me square both sides of this equation. 4 equals 4. Oh my goodness, I've ended up with something that is true. Therefore, I proved that this was true. Now, I don't think any of you are likely to try to prove that -2 equals 2 in this way. But you can see if you start with something that's false and you do the same thing to both sides, you can get something that's true. And some people are going to get confused and think that you've proved the original false statement. Okay. Now you might say, I'm going to write both sides, but I'm not going to change them. I'm just going to simplify both sides. The way we're going to ensure that is we can only work with one side at a time. Every equal sign that we write in the body of the proof requires a justification. This one is not yet justified. So I cannot write an equal sign connecting the left side to the right side until I've shown that they are the same. So I'm going to pick a side and I'm going to start with that side and work to simplify it. Okay. So I think I'm going to start with the left-hand side. They look equally simple or complicated to me. So I'm going to say I'm working with this, just the left-hand side, and that's A plus B plus C. Okay. Now, since that was just copying it, that's pretty clear. This was just me labeling what the left-hand side is. But now, I want to write these vectors in terms of their components, because that's going to transfer me from working with vectors, which we don't know a lot about, to working with numbers, which we do know something about. So, I'm going to say this is A1, A2 plus B1, B2 plus C1, C2. Okay. Now, that equal sign needs a justification. Why is this the same as this? Well, it essentially boils down to because we said so. But we only get to say that if we actually said so. Here's where we said so. We introduced our objects. Okay. Now, a slightly more formal way of saying this, other than because we said so, is to say that this is because of the definition of A, B, and C. And I defined them up here at this stage in my proof. Now, I'm going to be a little bit informal. I'm going to write my justification just directly below the equal sign. That's largely just because I have limited space. It's also a fairly efficient way of saying this is explaining why these two things are equal. Another possibility would be that I could write this equals this, and then just continue here where I don't have a lot of space because of the definition of A, B, and C. Okay. I'm going to go ahead and be a little bit informal and just write it under the equal sign. You can choose whether you want to write it under the equal sign or off to the side after that statement. Okay. And now I'm going to continue going. Okay. I'm going to have to just erase the top part here. Okay. I'm going to pretend that I'm just continuing, but I've run out of board space, so I'm going to continue up here. This equal sign is continuing right after here, so I'm coming up to this line. So now I'm going to do this addition. So I'm going to say that's A1 plus B1, comma A2 plus B2 plus C1, C2. And I say, well, why is that true? There's not a whole lot that I have to work with vectors. Basically, I've got definitions. And this is a definition. This is the definition of vector addition. We've defined how we go about adding vectors. We add them component-wise. So I can say this is true by the definition of vector addition. Notice I am being careful here. It's vector addition. That's the definition. It's not the definition of addition, because that's an addition problem, but it's not the definition of addition for real numbers that I just used. I used the definition of vectors. So basically, at this point, until we've proved the other things in that box of properties of vectors, I don't have a lot that I know about vectors, but I have definitions. So I have the definitions of A, B, and C that I gave at the very beginning of the problem, and then I've got the definition of my two operations, vector addition and scalar multiplication. Everything else I'm going to use is going to be properties of real numbers, because that's pretty much all I know about vectors. Okay. So now, I'm adding that vector to this vector, so I'm going to go ahead and do that. So I'm going to get A1 plus B1 plus C1, A2 plus B2 plus C2. So these two vectors combine to give me this vector. That's using the same reason. That's the definition of vector addition. So I used it twice, once to combine A and B, once to combine A plus B and C. Okay. One thing that's really important here, the definition of vector addition was a definition for adding two vectors. And what you get in the components then is a sum of two numbers. So here the two numbers are A1 and B1. Here the two numbers are the component of the first vector and the first component of the second vector. Second component of the first vector, second component of the second vector. Those parentheses are necessary. Okay, that's actually the crux of this proof. That's why we're going to have this associative property. Because what I'm going to do now is I'm going to say within each component, this is just an addition problem involving real numbers. With real numbers, I know that I have an associative property. So I can say that the number A1 plus B1 plus C1 is the same as the number A1 plus the number B1 plus C1. And same thing here. This is A2 plus B2 plus C2. Okay. Now, my reason here I'm going to be very careful of. I just used the associative property. If I stop there, feels like I'm going in circles. Because what am I trying to prove? The associative property. What did I just use? The associative property. You can't use the thing you're trying to prove the thing you're trying to prove. I didn't. I'm trying to prove the associative property for vectors. I just used the associative property for real numbers. So I need to be very clear here. This is the associative property of real number addition. I can use known facts about numbers when I don't have a whole lot of known facts about vectors. And that really is the crux of the proof. We're not quite done yet, but I need those parentheses there because basically the fact that I have this associative property says that vector addition is nice. It behaves kind of the way we would expect addition to behave. Why is it nice? Well, because I built my vectors out of numbers, and numbers have nice properties. So when you build vectors out of things with nice properties, sometimes the things you build inherit those nice properties. Okay? But that's why we have this associative property, because we constructed our vectors out of numbers, and because we defined vector addition to be done at the component level, at the level that we're dealing with just numbers. Okay. In general, as you're going through these properties, and you will be asked to prove some of these properties in the homework, as you're going through these properties, if you're trying to prove the commutative law for vectors, and you don't use the commutative law for numbers, you didn't show enough detail. Whatever property for vectors you're trying to prove is going to be true because there's a corresponding property for numbers. Make sure that that's included. Okay, so now I'm going to just keep going here. I could, if I wanted to, stop here and say I've simplified the left-hand side. I'm going to now start new equation, start with the right-hand side and simplify it. That would be what I call the 3-paragraph method, where you say, here's the left-hand side, new paragraph, here's the right-hand side, and then you look and you say, oh, I simplified them to the same thing. Paragraph 3, left-hand side is equal to right-hand side. The other option is what I'm going to do here. I'm going to just keep going and hope that I eventually arrive at the right-hand side. So I'm going to say this is A1, A2, plus B1 plus C1, B2 plus C2. What I just used was the definition of vector addition. Definitions work both ways. It's easier to see that, hey, if I add these, I would get this. Well, this is the result of adding these two things. So I can say this is the definition of vector addition. And then I'm going to do that one more time. I'm going to say this is A1, A2 plus, and I'm going to split this up. I'm going to say this is the result of adding B1, B2 plus C1, C2. Okay. So that's also the definition of vector addition. And then this is going to be A plus B plus C. That, of course, is the definition of A, B, and C, which is our fancy way of saying because we said so at the very beginning of this proof, and that's equal to the right-hand side. Okay. So I started with the left side, I simplified it one step at a time, arrived at the right-hand side. You'll notice all that I used were definitions and properties of real numbers. Okay, This video's been going for a while, so I'm going to stop it here. In the next video, I'll pick up with a little bit of talking about why I require this painstaking detail. Okay.